in some sense, maybe a lot of us don't really believe in real numbers the same way we believe 1, 2, 3, 4, 5. So this incompleteness result that I just told you probably doesn't convince most people as much as Gödel's. However, when you take it together with all the physical arguments that I was giving you against real numbers and the neo-Pythagorean hopes of having this digital physics where, you know, as Ed Fredkin says, all the laws of physics are there. A physical system just has a finite amount of information, and you know all the laws, and you know the state completely and exactly of a physical system. And that's a nice model, you know. In real physics, maybe we will never know all the laws of physics, plus the state of a physical system, if it involves real numbers, is not something we can have on a piece of paper. But if you believe in digital physics, if this universe obeys digital physics, or if you can make a toy universe which is good, even though it's not this universe which obeys digital physics, then you would have the whole thing in your hand, you see, which would be nice intellectually, right? So this has some other connections, you know, speaking from a philosophical point of view or humanistic point of view instead of as a technical mathematician. Let's look at our current technology. Our current technology is digital. The big advance was going from analog to digital, right? CDs are digital. Old, what was it, 33 RPM records were analog. So that's going from real numbers to digital. If you look at DVDs, they're digital, right? Which is why movie companies hate them, because you make perfect copies. The old videotapes are analog, which means every copy is in poorer condition than the original. So the movie companies felt safe that you couldn't steal their content, is that the word, or intellectual property, or whatever the word is. So on the one hand, that's the big technological success of our time. Now let's talk about science. The most successful science of our time at this moment is not physics, that was a long time ago. It's molecular biology. And the big thing in molecular biology is DNA. Now what is DNA? I think DNA is digital software. Really. That's what it really is. And so from this point of view, a human being is, what is it? It's 3 billion base pairs. So that's 3 gigabases, which is 6 gigabits. And you have to divide by 8. So it's almost a gigabyte of digital software. You know, it's 6/8 of a gigabyte of digital software is you. So I think that it's sort of fun to, this view may be wrong, this new digital viewpoint may be wrong, but I think it's sort of fun to pursue it as far as you can and see where you get with it. And of course, this is the kind of mathematician, obviously, who doesn't do topology, right? This is the kind of mathematician who likes, for example, elementary number theory, not analytic number theory, maybe because already you're dealing with real numbers. But, you know, this is an old viewpoint in math. There's this tension which goes back maybe to Zeno's paradox between the discrete and the continuous. You know, if you keep dividing something, right, if you keep breaking something in half, the ancient Greeks asked, there are two possibilities. Either you can keep on breaking it in half forever, so then everything is a continuum, physical reality is a continuum, and Democritus, and that's why Zeno claimed that we got into trouble with the continuum, and Democritus said, no, at some point something will be indivisible, which in Greek I think is atomos or something, I don't know what it is. Right, so those are the two logical possibilities, you know, so this is doing science by pure thought without having to do any experiments, which is very impressive. But it took 2,000 years to see that it sort of works, you know. So I think it's sort of fun to pursue these ideas. They may be completely wrong, but what's interesting about them is that they're so different. And so I wanted to come here and commend this whole big package because I think there are a lot of pieces. So there are increasingly, for example, there was a review in Nature of a book. Well, you know, quantum information theory is also, you could say it has something to do with this digital philosophy or digital physics. It's not an extreme case. If I talk to Charles Bennett, or, you know, he thinks that one of the big contributions of quantum information theory, where the goal would be to do quantum computation, right? I don't know if that's possible. But is the idea that information is a very important concept in quantum mechanics. And this is new because in 1924, quantum computation and quantum information theory don't change the rules of quantum mechanics. It's still 1924 quantum mechanics in a way, you know. But they use a new viewpoint. They say that it's fruitful to look at the notion of information. Now, it's not actually digital information in zeros and ones. It's something more complicated. But I think, you know, maybe the reason we're coming up with these new ideas, which are very speculative, is because we don't have enough theoretical data to clues. to come up with a more reasonable physical theory, right? But, superstring theorists have been doing this already for a while. There's a criticism of superstring theory, which is that there's no contact with experiment, right? There are no predictions they can make that anyone can test. They argue that the theory is compelling for many other reasons, but the truth is that traditionally science, it helps if there's some way of confronting the predictions with experiment. And for the moment, since no one has the money to do experiments in the energy range that you would need for superstring theory, it becomes more like theology, right? Well, this is a similar, here, since at the moment, we don't have exciting new experimental data about black holes or new subatomic particles to suggest the direction to go. This is an attempt to sort of use pure thought and argue, from a priori that the universe has to be discrete because the human mind finds that more comfortable. But the physical universe doesn't have any reason to be nice to us. But I think it's fun to pursue these ideas just as speculations. So I guess that's about it. Thanks a bunch. I'm sorry I was late. Does anybody have, you can throw tomatoes, you can ask questions, you can make comments. Yes? Or do you want to control the process? Go ahead.
Okay, first of all, I want to thank you.
My pleasure.
And of course, questions, comments are welcome, and even digitally, we can. Those that are not here can put questions through the web. And
oh, we're on the web right now?
I believe so. Yes. So at this moment, there is no question in the web. So maybe in the audience, some question.
Or you can just say you think this is completely crazy, and I'll have to agree. Yes, but it's
no. I don't know if it's crazy. No, my
it's
question
not even
is
crazy.
My question is looking at the state of science, namely mathematics and physics today.
Today, yes.
Do you have the feeling that without real numbers we would have had a path which is different from the one we had, certainly. But do you have a personal feeling that we would have gone more far or the same, or that's a sort of completely different world?
Well, look, if that's a good question. Let's say you don't believe in real numbers, but you can still do partial differential equations on a grid, right? When you actually do numerical solutions of partial differential equations, you discretize it on a grid, and you don't use infinite precision reals. You use floating point arithmetic in a computer, which is finite precision. So I mean, in other words, differential calculus becomes the calculus of finite differences in a sense, right? And it would be pretty much equivalent, if you have enough precision and you make the grid fine enough. So in that sense, who cares? It doesn't make any difference. It could be that nature is discrete, but that it's, the number of digits of precision is so high that we could never tell the difference. I don't know if I'm answering your question in any reasonable way. If you look at atoms, atoms look fairly discrete, even though you can argue from quantum mechanics that actually atoms are continuous because a particle is also a wave, which is true.
I'm just more thinking about the concept of real number, whether it was helpful,
I think it was helpful. I think it was a good simplification. What interests me, about Leibniz as opposed to Newton, is that Leibniz not only did the calculus, presumably Newton did it too, although I'm not convinced, because the Principia, what Leibniz said against Newton in the Principia, you see, Leibniz had done calculus, and everybody had learned it on the continent from Leibniz. And then one day Newton says, you stole it from me. And Newton hadn't published a word on the subject. And Leibniz says, what do you mean? I looked at Principia. Principia doesn't use calculus. Newton claimed he had gotten it with calculus. And Leibniz said, well, if you discovered the system of the world with calculus, you're going to explain it with calculus. It would be inevitable.